All right, let's take a look at example 9. So a young engineer notices in her plant that 1 kilogram blocks of brick are routinely removed from an 800 degrees C oven and are let stand to cool in air at 25 degrees C. Conscious about cost cutting and efficiency, she wonders whether some work could be recovered from this process. Calculate the maximum amount of work that could be obtained. The CP of brick is zero point 0.9 kilojoules per kilogram Kelvin. Before I even start the problem, so one thing I want to make a note just in case I need it is we're given the CP of brick. Right, brick is a solid. And so typically for solids, we can assume that CP and CV are equivalent. Okay, so typically we can assume that CP is approximately equal to CV. Right, our solid's incompressible, so CP and CV are essentially the same. All right, so the situation then that we have is that we have some brick that's pulled from the oven. It's going to be at some temperature of 800 degrees C. Okay, and it's placed in the atmosphere at 25 degrees C. So I'll take my brick to be my system, and I'll assume that the surrounding atmosphere, my surroundings, right, could be treated as a bath. Okay, that it's this infinite reservoir. So my brick sits out in the atmosphere and it cools until its final temperature is 25 degrees C, which is the same temperature of my surrounding atmosphere, or that bath. Okay, that my brick and the surrounding atmosphere are in equilibrium. Okay, so if we want to calculate the maximum amount of work, the maximum amount of work is going to occur when I have a reversible process. I have a reversible process when Sgen is equal to 0. Okay. Well, Sgen, okay, is going to be equal to the sum of delta S of my system. Okay, I'm going to write it as total, my extensive delta S of my system, plus delta S of my surroundings, right? And that's going to be equal to 0. So let's take it one term at a time. So let's start with my surroundings. Okay, so I need to calculate delta S of my surroundings. Well, okay, and this is, again, total, just for, clarity. So for my surroundings, okay, I'm going to take my surroundings to be a bath. Okay, and therefore, right, so for my bath, temperature is constant. Delta S of my bath is going to be equal to Q bath over T bath. Okay, now Q bath, in this case, heat's going to be received by my bath. So the amount of heat received by my bath is the opposite of the heat, received or given by my system. All right, so Q bath is equal to, and I want, total. So this is going to be negative M times Q of my system. All right, so heat removed from my system equals heat gained from my, heat removed from my system is equivalent to heat gained from my bath, right? Hence the opposite sign. So Q bath is equal to M times Q system. T bath, okay, following my diagram above, I'm going to write as T2, right, which is that at the final state, the temperature of my bricks equivalent to the temperature of my bath, my surroundings. All right, so now Q system. So for Q system, I'm going to write down a first law energy balance. I'm going to write that delta U is equal to Q, and I'll just put a system on here, plus W. Okay. Now delta U is equal to integral from my initial to final state, CV dt. Now we said at the start of the problem that for a solid we can assume Cp and Cv are equivalent, and here Cp is given as a constant value. So delta U we can just take to be Cp T2 minus T1. All right, and in writing it this way, the assumption is that delta U is approximately equivalent to delta H. All right, so I get delta U is equal to Cp T2 minus T1. so that Q system then is equal to Cp T2 minus T1 minus W. Okay, so I end up with delta S of my surroundings, again, total is equal to negative M over T2 times Cp T2 minus T1 minus W. Okay, and I'm just going to distribute just to make sure I don't end up with a sign error. When I plug this into my final expression, this would be negative M over T2 Cp T2 minus T1 plus MW over T2. Okay, and I just want to distribute just so that when I plug this into my final expression, I make sure I have the sign right. All right, now let's look at my system. So for my system, I use my definition of entropy. Okay, so for my system, I have the ds is equal to my reversible heat exchange, all right, my heat exchange from a reversible process, Q reversible over T. I got to put a D in there, right? Differential. Now, in terms of the heating or cooling of a brick, right, I'm going to assume, or I would assume, that the heating or cooling takes place at, you can equivalently use constant pressure or constant volume, right? If we assume that heating takes place at constant pressure, then dq reversible is Cp dt. If you assume that it takes place at constant volume, then the differential of Q reversible is Cv dt. But since we're assuming that Cp and Cv can be taken to be equivalent for a solid, either would get you to the same place, right? Whether we assume it's isobaric or isochoric, we would get to the same result. And so I'll just plug in the expression for isobaric, so then we're using Cp just like before. So if I assume that my heating or cooling takes place at constant pressure, which again for solid would be equivalent to constant volume if we assume that it's incompressible, then I get that dq reversible is equal to Cp dt, and that's divided by T. Okay, so therefore, delta S of my system is equal to the integral of Cp over T dt, integrating from my initial to my final temperature. We assume that Cp is constant, so assuming Cp is constant, then delta S of my system is equal to Cp times log T2 over T1. And if I want the extensive value, that's delta S of my system total is equal to mCp log T2 divided by T1. All right, so then putting together, okay, so plugging it together, so putting it together, okay, we have delta S surroundings total plus delta S system total has to equal 0. So we have the mCp log T2 over T1. So that's positive. Then minus m over T2 Cp T2 minus T1, then positive m over T2W is equal to 0. Okay. The first thing I'll do is I'll divide through by m, so I'll kill m. Okay, so that's great. And then I'm going to multiply through by T2 just so I can isolate W. So I'm going to have T2 times Cp log T2 over T1. Come on. Minus Cp T2 minus T1 plus W is equal to 0. So W therefore is equal to Cp times T2 minus T1 minus T2 Cp log T2 over T1. Alright, so now let's go and evaluate it. So I've already typed some of the values in MATLAB. So T2 was our final temperature in 25 degrees C. So I convert it to Kelvin. Why? Because here I have a ratio of T's, so that needs to be in absolute units. T1, bricks originally at 800 degrees C, convert to Kelvin, Cp of 0.9. So in the expression as I have it written here, actually I have the first term written, so negative T2 times Cp times log T2 over T1 plus Cp times T2 minus T1. So running units of W will be the same as Cp times T, which is a Kelvin, so kilojoules per kilogram. All right, so Cp is in kilojoules per kilogram. So solving, we get the W is equal to negative 353.8281 kilojoules per kilogram. So that's the maximum amount of work that I could extract from the process. All right. Hope that works, right? And hope that helps. And I should say it's negative. So negative means that it's work done by my system on surroundings, which is exactly what we want, right? So negative W is heat done by my system on surroundings, or work done by my system on the surroundings, which is what it seems they're attempting to accomplish. Hope that helps.